All right, I'm going to go ahead and actually begin this practice exam that we're going to be working on. I'm going to work through the multiple choice and then the free response. So, as far as fundamental units go, let's get really clear. First of all, what I'm going to do here is I'm going to actually write out every single one of the ones that we do know. So joules, you should know, are newtons times meters. By the way, the newton, you should know, is kilograms meters per second squared. The reason I know that is that force is MA. M is kilograms, A is meters per second squared, and that's how I get newtons as my unit. Pascals, those are a unit of pressure. It actually turns out that those are newtons per meter squared. So those aren't going to work. And it actually turns out that ampere is the fundamental unit. By the way, the other fundamental unit, so we have amperes, we have kilograms, we have meters, seconds, candelas, and moles, and there's one more, let's see. And lastly, we have temperature, Kelvin. All right. Now for number 2, we want an estimate of the magnitude of these forces. So let's just think about some magnitudes here that actually won't work. First of all, 0 newtons and 1,000 newtons and 2,000 newtons are not going to work. Here's why. If this were 1,000 newtons and this were 1,000 newtons, sure, this would give us 0. And same with this. If we had a vector going this way and it was 1,000, that would work. So basically, you're only going to get 0 if you have 2 anti-parallel vectors. Now for the 2,000 newtons, you need them to be completely parallel vectors. Now here, let's actually try to figure out what's going to happen. So here's what I would do. If you remember, there's a technique called head-to-tail addition. So I can take this vector, and I'm just going to move it here. And we're going to take the head of this, connect it to the tail of that. And so the resultant vector is going to be this big, definitely less than 1,000, or definitely less than 1,500. So that's not going to work. So it looks like our resultant vector is in fact 1,000. Okay. So that's number 2. Again, it's an estimate. Okay. All I know is that this vector is definitely shorter than, how to say this? This vector is 1,000. 1,500 is way bigger than 1,000. This resultant vector is not bigger than this vector. Therefore, it can't possibly be 1,500. And the only choice we have left is B, 1,000. All right, now we have a object subject to a constant resultant force. Let's be clear. The word constant resultant force means that we have an F equals ma on the object, and this is constant. And that implies that a is constant. Well, we have some formulas for when acceleration is constant. Also, we're told the object is initially at rest, so I'm going to take that into account with my formulas. So I know that these formulas are true. And there's one more. And let's be clear, since u is 0, there are a number of terms that drop out. This term drops out because u is 0, so does this, and so does this. So what this tells me is if I were to graph s against v squared, I would actually end up getting a nice steady line, according to equation number 3 that we wrote here. Now, we've got the velocity time graph for an object subject to a constant force. Again, a constant force, let's be clear. Constant force implies that acceleration is constant too. And let's remember the slope of velocity graph is the acceleration. So that actually gives us this choice right here. A nice constant acceleration that's not 0. So that's number 4. We'll continue 5 through 8 in the next video.